We present VibGrasp, an active haptic shape rendering method and a supporting haptic glove that synchronizes spatiotemporal vibrotactile feedback across multiple phalanges with 1 degree of freedom kinesthetic feedback. We hypothesized that vibrotactile patterns differing in duration, stimulation area, and transition profiles which are combined with hand flexion can evoke the sensation of grasping different object shapes. To examine this, 5 vibrotactile patterns with different spatiotemporal profiles using phantom sensation are designed for primitive shape perception study. 3 primary vibration patterns were established based on the vibration area: individual point activation, activation with 1D stationary phantom sensation on interproximal phalanx, and activation with 1D apparent haptic motion. Next, we divided the individual and SP patterns into discrete and continuous subcategories based on vibration continuity, resulting in 5 patterns. For cylindrical shape perception study, we designed 3 vibrotactile patterns with different transition profiles of the apparent haptic motion, producing either an early or late increase of vibration intensity. To effectively render the haptic feedback, the exoskeletal glove is designed to enable finger flexions through ankle routing, leaving the ventral side of the finger open. Distal phalanx symbols and proximal phalanx units of index and middle fingers incorporate 4 haptic motors to provide vibration, and a tendon-driven kinesthetic haptic module attached on the wrist provides feedback for hand flexion. We enabled vibration to be transmitted through the proximal phalanx units and the distal phalanx symbol, allowing perception on the ventral surface of the fingertip while keeping the skin unobstructed. To investigate how spatiotemporal vibrotactile patterns along with kinesthetic feedback influence participants' perception of object shapes, we conducted shape perception study. While provided with 5 haptic patterns including I-discrete, I-continuous, SP-discrete, SP-continuous, and AM, participants were asked to select 1 out of 3 shapes they are most likely to grasp and the area and duration they felt the vibration. Next, while provided with 3 haptic patterns with different transition profiles of AM, including linear, PP concentrated, and DP concentrated, participants were asked to select 1 out of 3 cylindrical shapes they are most likely to grasp. For primitive shape perception study, we found the consistent relationship between haptic patterns and shape selection, supporting the hypothesis that our haptic rendering methods modulate perceived object geometry. For cylindrical study, the linear pattern most strongly favored the baseline cylinder. DP concentrated showed the higher preference for the prolate shape. For the vibration area and duration selection, continuous patterns exhibited an upward shift bias, with the highest reported phalanx at each stage tending to be more distal than the stimulated one, while others show relatively higher accuracy. Lastly, we evaluated the user experience of VibGrasp by comparing it with 3 haptic methods and devices from prior works during VR grasping. We compared VibGrasp with passive haptic rendering methods using a different device, which are vibration only, multi-phalangeal kinesthetic feedback only, and vibration and kinesthetic together. The results show that VibGrasp showed higher subjective ratings for several categories of user experience compared to prior methods,